So yes, my name is Brian Ward. I'm a software engineer in CCM. I sit on the third floor, roughly above where the food was today. And I'm going to be talking, I think on the paper it said Introduction to Foreign Function Interfaces. Yesterday someone said, what's a foreign function? Which I think is a fair enough question. And so I have a subtitle of how to have users in language X, but you still get to write your code in language Y, right? A foreign function for our purposes is any function that isn't in the language that you want to be writing in right now at this moment. With that being said, I do have a couple of disclaimers. So the first thing is that I'm really going to be focusing on the case where you have some compiled code, right? Some code written in C, C++, Rust, Fortran, and you're interested in calling that code from a higher level language like Python or Julia. You can do it in the other direction, but I think for the use cases we have here, this is the more useful one. It's also the one that I know more about, and I think I can sort of give you some rules of thumb that will hold in general that probably isn't true in the other direction. Also, the examples are primarily using a mix of C and C++ and Python. My emphasis is on a style that should work sort of regardless, and I'll try to be really careful about calling out when something is specific to Python versus when it's a sort of particular example of a more general style that would work in other languages. So really first, why do you need a foreign function? And there are probably people here who've already worked with some of these systems and might already know. But there are a bunch of reasons. The two that I find most frequently are you're writing something in something like Python and you need access to a system library of some kind. So you need to ask some information for your operating system. And the only way to do that is through a library that was implemented in C, most likely, for most operating systems. And then the other thing, and I think probably more common for people here, is you want to write performant code, right? You're writing some sort of simulation code or something else, and you want to be able to write that in a compiled language where you can take advantage of, for example, all the things in the talk earlier, but you want it to be accessible from a language where there are more users, right? So something like Python or Julia will probably have an order of magnitude more draw than something in C or Fortran, for example. So just to make everything concrete, I'm going to present some sort of silly C code. This is the C code that I'm going to pretend is very expensive and that we're going to be wrapping for the first part of this talk here. If you're curious, all it does is just calculate E given a certain number of iterations. There's nothing particularly interesting about it besides it has one input, it returns a double. There's no pointers or anything. We'll talk about those sort of at the end of the talk, but for now we're just going to have a nice simple arithmetic function.
Or something. What does it do?
It converges to Euler's constant.
Oh,
to E.
Euler's constant. Just E? No, gamma like 0.58 or something.
No, 2.7.
Oh, so E to E, right?
E,
got
it. Yeah, Euler has too many things named after him. So before we sort of talk about the specifics of wrapping sort of anything in particular, I think it's important just to give a sort of brief introduction to sort of how your computer kind of works at a low level. This ends up being sort of important for calling things later on. And so there are a couple ways where code can be reused, compiled code can be reused on your computer. The first is a static library, which is you have some compiled code that's sort of sitting on disk. And when you compile new code, it essentially just cuts and pastes. It's a little more complicated than that, but not really, that code into your executable and runs. And then the alternative, which is what we're really talking about today, is going to be shared libraries. And so a shared library is some code that's been precompiled, and it can actually be loaded at runtime and accessed. So this is what you get out of your, if you're using GCC or Clang, this is what you get when you pass the -shared flag. For a lot of uses, these are loaded at the startup of a program. And that's where a lot of the usage of the word shared comes from, because you can actually have multiple programs loading the same library at once. We're really going to be focusing more on the runtime aspect of it, where when the program, when Python starts up, it's not going to know about this code, and we're actually going to tell it about it later. On different operating systems, these go by slightly different names and have slightly different extensions. So I'll be using shared library pretty consistently. They're also called dynamic libraries, or especially the Windows world calls them dynamic linked libraries, but they're all the same kind of object in the end. And ultimately, everything we learned today is going to be using a shared library, right? You might not always see it. You might not always know that it's there, but that's where this is all going to be happening at a low level. And so to talk about sort of how those things work, it's important to understand what actually happens when some compiled code on your machine wants to call a function. And you may be writing in C++ that has all these abstractions like objects and these other tools that you use to write your code. But ultimately, when something is compiled down, the only thing you end up having left is just a straight line of instructions, right? So you just have some code, and then that code will have labels interspersed to it. And the sort of one abstraction we do still have is this sort of handshake around what is a function. And so when you're dealing at this low of a level, what a function really ends up being is an agreement on how I'm going to prepare some inputs, and then a place that I'm going to jump to. And then that code is going to assume I put my inputs in the place I promised I would, and it's going to run off. And then when it's done, it's going to jump back to me. Now, this is called a calling convention. They're a very complicated, interesting topic. You probably talk for an hour just about them. I don't want to do that. So I'm just going to say for now that assume that there's one of them. Assume that your computer already knows what it is for your operating system and architecture, and assume that it's all sort of fixed and nice. Now you can guess by me saying assume that none of those statements are actually true, but they will be for the purposes of this talk. And so I'm going to actually jump. So some people were commenting on my strange font choices, and that's because this is actually a terminal. And so I'm going to jump into a demo. So we'll see how well this works. Yeah. Yeah. So I have a couple files in this folder here. The Euler file is the one I showed you before that contains that one function definition. And then I also have here a test file that I'll show you real quickly. All it does is read in an argument, calculates that, uses that as the number of iterations, and then prints the output. And so if I make it real quick, I can then show you, if I give it only one iteration, it gives me a really bad approximation of E. If I give it maybe 3, maybe this is good enough for an engineering student. And if I give it 100, then you essentially have converged to machine precision for E. So, it works. It does what it says it does. And all the I'm going to give you a link to the code at the end of the talk. All of these folders will have a test file in them that will do something roughly like this. What I'm actually here to show you about, though, is a fun tool that gets very useful when you're dealing with shared libraries. So actually, I'll show you after I ran make, you'll see now I have this file called Euler.so. .so is the shared library object extension on Linux. On Mac, this would be .dylib. On Windows, it would be .dll. But they're all the same thing. And there's a very useful command called nm. So what nm does is list symbols from object files. Now, if we think of those symbols as sort of those labels I mentioned a minute ago, it'll essentially tell you what functions are in an object file, where an object file just means some sort of compiled code. So a dynamic library, a static library, or even a final executable. And what I can do from this is I can say nm, and I can give it the name of my library, and it will list a bunch of stuff in there that the C compiler put in. But in particular, I'll highlight this line here. That is the label and actually the location in memory of this object of that function I just wrote Euler. These letters all have interesting meanings. I recommend if you're interested, read the man page on nm. The important thing here is that T means that it's a well-defined symbol, that I know where it is and I know how to access it. I can also, if I clear this real quick, I can also actually ask the same question of my executable. You'll see even more junk the compiler put here. Down here is main. That's a pretty important function. And then up here, you'll actually see Euler with a U next to it. U means undefined. And so you sort of have a keyhole and a key, right? Like this, at startup time, this executable will load that shared library. It will get that address, and then it will run off and keep going. Yep.
Is a static library instead of a shared library? Would Euler be defined?
Yes. So yeah, if it was a static library during compilation, it would actually take that code and relocate it into your binary, and then your binary would just have it there. Yeah, that's a good question. So I'm going to jump back into the slides now. Oh yeah.
So what environment variables define a path where usually this is looked for? So if I'm missing a dynamic library somewhere, what environment variables should I look first to update to find the stuff I'm missing?
So this is actually an interesting question. On Windows, it's just the path or the folder of the current executable. On Linux and Mac OS, you can usually define a couple of different things, some of which have different impacts. So like the most common one you'll probably see is LD library path. But that can also then make it so that you're pulling libraries that it was previously able to find. It might now find different ones. So there's some subtlety there. What I'm doing for all of these demos is something that you can do, which is you can basically tell the executable actually what the full path is. And then if you're compiling on your machine and you're not going to be moving files around, it just knows where that shared library is. So that's called the R path or runtime path. But yeah, if you have more questions about that, we can talk after. It's like that's one of those things that there's a bunch of answers with different trade-offs and also a lot of operating system sort of dependence. So that previous demo was nice. I wrote a function called Euler, and it actually appeared in the library called Euler. And that will work if you're writing C code, and will probably not work if you're writing anything else. So for example, if you want to write C++, you'll have to deal with some different things. So I'm going to jump into a different demo to show those real quickly. So here I have a different set of files. If I show you what is in Euler.cpp, you might be disappointed because I'm just pasting in the text of that C function. So you hear some people talk, they say that like I write C++ like it's C. This is quite literally doing that. And so the test file is also, it's the same like meaning, it just has different stuff because I wrote it in C++. But if I make test, you'll see that I get those same outputs and I can run test 100 and I'll get E, it all still works. But now if I run nm on that shared library that was created, you'll see, so Euler before was somewhere up here and it's missing. And in fact, if we look, it's embedded down here, but there's some stuff around it. And so this is known as name mangling. And most languages that use a more complicated language model than C will end up doing some kind of name mangling. And so in particular, C++ does it to enable things like namespaces and overloading. That's actually why there's an I at the end. It's because this function takes in an integer. And so when you're down at this level, there's no such thing as multiple labels or like the same label pointing to multiple places. So you need to make all the labels unique. And so C++ mandates that name mangling happen, but importantly, it doesn't tell you how to do it. And so every compiler on every different operating system will do it slightly differently. It's not guaranteed to work with each other. And so this can be a problem for a lot of the stuff we want to do later, where we kind of need to know what the name of the thing is. And so, and I can also show you that C++, of course, because C++ knows about itself, it knows what its own names are. So if I list all the symbols in the test executable, first you'll see that C++ puts a bunch of junk there. And then second of all, if I scroll up, you'll see, oh, where is it? I might have already missed it. There it is. So C++ internally will use the same name mangling, but if we want to talk about it to the external world, either we need to sort of backwards, like reverse engineer it, or we need to look at some other options. So I have here yeah.
Does nm stand for name mangler?
I'm not sure, actually. I think it might. So nm does have a flag that will print out the unmangled version of names, but that sort of defeats the point of my illustration here. So I didn't pass it. I think it's -D for demangle. But I think it stands for name, but I'm actually not sure. And the man page doesn't give you the history. So here I have, sorry, I meant to go into the other C++ folder. So here I have the same thing. And if I show you Euler again, it will look exactly the same, except I changed one thing, which is I wrapped this definition in, extern C. And this is a feature that is available in most languages. It's often called just this. So in Rust, it actually uses the exact same syntax, extern C. In some other languages, you just have to look it up in sort of your language manual. But this does a couple things. For one thing, in C++, it turns off demangling. And it basically is telling your compiler, I'm going to want to call this function either from C or like it was itself written in C. And so if I run make test, the test executable is the same between these last two things. Test will still work, but now if I look at nm of my library, you'll see, okay, we're back to just good old-fashioned Euler, even though if you look up here, I still was using G++, the C++ compiler. And so extern C is like a very important feature when you're dealing with this sort of thing. It's nice to know. You can save yourself a lot of headache. There are certain things you need to know about when you're using it. So if I go back to my slides, there are features that are disabled if you're using this. So for example, overloading. If you have a function named extern C, you can't have overloads of it anymore in C++. And also, if you're sort of being a good citizen of the world, you should try to make sure that these are globally unique names. So if a user has a bunch of libraries and they're loading all of them, and you might be defining some common name, then when your package gets loaded, it might smash over someone else's definition that we're already using. So it's good practice, to put like name of my library underscore name of my function on these extern C functions to avoid that issue. I mentioned here Rust is the same. Fortran also uses some forms of name mangling. Usually it's just appending an underscore. I don't write Fortran myself. I understand there's a flag you can use to disable that. And there's also different ways where you can sort of tell Fortran like, hey, I want to interface with C. And so for the rest of this talk, I'm going to assume we have some compiled thing that we used whatever we need to do in our language to make it sort of look and feel like C. So now that we actually sort of know what it means to call a function on a really low level, how do I actually do that in a language like Python? So I'm going to show you first sort of what the goal is. So this will be the test program that I'll be evaluating everything against. And it's just a Python reimplementation of the same thing I was doing in C or C++. I'm just going to read in from the arguments a number. I'm going to call, so in this case, I have a library called Euler and the function's called Euler. So it's Euler.Euler. And then I'm just going to print out the result at the end. And so this is sort of what you can keep in the back of your mind as sort of the target for all of these things. The first thing I'm going to talk about is, I suspect, what a lot of people here might have already heard about, or if you have sort of Googled this sort of thing before, specifically for Python, you probably ended up on a page about the Python C API. And this is something that most languages will provide, a way to actually write, sort of code specific to that language using a C or C++ API. And then when you compile that object, like Python sort of just knows what to do with it. And so for Python, it's going to be the python.h header that comes with an installation of Python. I'm going to show you some code on the next slide, but I'm also not really going to talk through this code much at all. This is for two reasons. One is that I really did just copy it from the tutorial on python.h. I give you a link to that. And two is that the methods 2 and 3 that come up later in the talk, I think are things that I would recommend doing in almost every circumstance over this. But it's useful to sort of know what we're dealing with and sort of as a baseline. So I'll show you the code now. This is what we would need to expose that one function to Python. And in fact, it's only about half the code. I left out some that I'll show you when I jump into the demo. But essentially, I include whatever code I want. And then I have to write these Python-specific wrappers that use Python logic to handle it. So I have to take in these Py objects, and then I have to parse out an integer into them. And now that I have a normal integer, I can call my normal code, and then I need to wrap it back up into a Python double and return, right? And so I'll jump into the demo now, but this can actually be, especially as you write more complicated code, there can be a lot of extra stuff you have to do. You have to manually invoke the garbage collector or reference counting and these sorts of things. So I'll actually show you the full code. Everything after this line, which is where I cut off in the slides, is essentially just registering the model in Python. So again, this is all just taken sort of from the Python documentation itself. And as you can see, it's about 30 lines, most of which is sort of registration or boilerplate for Python. And then the other...
Does that gets compiled as a C++, as another .o that gets linked into your library, your shared object, and then, well, I guess you're going to show us that.
Yeah, so the next thing it's going to show is how this actually gets built. So if you're using Python, or if you're using this approach and method 2 in most languages, you'll then be using the build system that sort of comes with the language. So in this case, to build this Python extension, I wrote a setup.py. And that basically, I have to register this extension and say, when you're installing this module, please build these extension modules. This is just how Python does it. It would be different in other languages. But now, if I can actually even show you what's in my make file here, all I'm going to do to build it is just call that setup.py. So now if I run make, you can see all my make did was run this, and all the rest of this was actually done by Python itself. And this is one of the first things that I think is good to know about these approaches, is that I didn't specify any of these command line flags. These were all put there by Python. And I could have tweaked them more in setup.py if I wanted to. But when you use these sorts of approaches, you might have to, depending on your language, force whatever build system you use into the world of the language you're dealing with. And that can often be kind of annoying. Like if you really don't want to use O2, you really have code that, like you've benchmarked and it only really runs well on O3, you have to figure out how to communicate all that again, because presumably you already have some CMake or something that you're using on the side. But that all being said, I can now run Python test.py. And for the first time in this talk, we've actually done a foreign function interface call. So this is calling into a C library. It's running that C code and printing it out in Python. And so that, it works. You can do this approach. And there are certain reasons why you might want to, but we're also going to talk about some others. So let me go back. I believe I have, so I have some pros and cons to discuss. One thing that is sort of underrated, I think is nice, is that with these approaches that are sort of, you're using, in this case, I was using pip or Python. If you were using Julia, they have a thing called JLLs. When you use these, the library that gets built ends up in a place where like Python always knows where it is, right? It ends up in the same place that if you pip install NumPy, it goes there, which can be really helpful to, to not have to try to debug those sort of path issues that Mattia kind of alluded to, where it doesn't know where the shared library is. I've listed this as a pro, that the build process is handled by that language's packaging system. It is also definitely a con if you're depending on other outside libraries or you have a sort of complicated or difficult build system. Trying to write that into a setup.py file is not fun. So that's sort of, depending on how complicated your code is, that is either a pro or a con. And the nice thing about this approach is you can actually write some code that in the compiled code can really leverage high-level constructs in the language. Like if you wanted to write code that actually dealt with the Python list object, python.h is probably like a good way to go. Some cons, some of these are probably obvious just looking at all that code. You need to learn the low-level API for the language you care about. And this, that was written in C, but it was really written in C plus a bunch of macros, plus a bunch of other things you have to keep track of in your head. And it will be different for every language. So if you want to look up the MATLAB C API, it will be using different macros and different constructs that you have to all fit together. And they can sort of include new gotchas. So like in Python, you might have to deal with reference counting. And then also, this is building a shared library, sort of to Alex's question. This is actually building a shared library that is then sort of specific to Python. So you're not going to be using the same library in Python and Julia or C. You're going to have different built objects for different systems, and there's no sort of reuse there in terms of the compiled code. So the next option, and I think this is probably where a lot of people also go next, is a tool that will sort of automate some of this for you. And so these are often very specific to, you have a sort of one pair of language to language. And so if, for example, if you're using C++ and you want to write a library that can be exposed in Python, then for that one specific pairing, the most common option is probably pybind11. And what that does is sort of automates a lot of that generation. So it still ultimately is using that same underlying API as the step before, but it sort of automates a lot of the boilerplate for you. So I can show you now, actually, it'll fit on one slide. This is the entire equivalent of that code in pybind11, right? So I include the pybind header, which you have to install separately. It doesn't come with the language. And then I just have to define a module and just give it a pointer to this. And it uses C++ templates and macros to sort of figure out what the types are, how to translate from a Python object and back, all that sort of stuff for you. And so these can be really nice, especially if you're dealing with higher level concepts. So like if you had an object-oriented API in C++, pybind11 can actually translate that into an object-oriented API in Python. But again, it will be very specific to the language that you want to talk about. So if you were using something other than C++, I also have to actually, sorry, I have to activate, I have to remember to do this because I haven't installed a specific environment. So here I have that file I just showed you. The setup.py here is actually almost exactly the same. I just had to say, instead of importing a normal extension, I had to import a pybind11 extension. And again, all this stuff just sort of comes from the getting started docs on those specific pages. And I can run make. And again, I have even less control now because PyBind is also inserting its own compiler flags into this whole process. Because again, all I'm doing is just running setup.py build. But the result does still work. So I can run Python 10, or 100 or whatever. I think at 100 it's already converged. Yeah, I can sort of I can call my code and it will all just work. But like I said, there are sort of some obvious downsides. Like, sorry, I have to get back to my. Oh.
The makefile doesn't come for free there. You wrote a makefile that said essentially Python 3 setup py.
Yeah.
That's it.
Yeah.
Okay.
And I just wrote that sort of for consistency. So you can just go into any folder in this and run make and it will work. You don't have to do that, obviously. Yeah.
Yes, isn't there also a way to use PyBind 11 and not have to use the Python makefile or any of the flags for the compiler directly so that you can compile your own objects and then force them in?
I believe that, yeah, PyBind 11 specifically, I think supports CMake and maybe a couple other options. So again, sort of in specific, yes, in general. So sort of to get onto this slide, the pros and cons are very similar to the first method, right? Things like the build system. But then also, like I said, this will install your package in a place where Python or Julia knows where it is, which is nice. And it also is nice because these can really some of these tools are really good at understanding higher level concepts in these two languages. So they can map really nicely from C++ objects to Python objects and back. The cons, so one of them is that build system. And again, that sort of depends on the language. And I think probably the overall con here is actually this third bullet point here, that these are often specific to a single language-to-language pair. So if you want C++ and Python, you can use PyBind 11. If you want C++ and R, you can use RCPP. If you want C++ and Julia, you can use CXXWrap. If you want Rust and Python, you can use Maturin. And like the list goes on. And as you can imagine, it's sort of like a combinatorially large space. And you would sort of have to know what you care about. So if you do genuinely care about, like, I have one language I'm writing my compiled code in, and I really only do care about one language for an interface, like I do think it is a genuinely good idea to find one of these tools, learn it well, and use it. But I don't think it scales as well as some other approaches, which is what we're about to get to. Some other cons, and again, these will be very variable depending on which tool you're using. So PyBind 11, you write this little piece of code and it uses macros and templates to figure it out. Some other tools that sort of fall into this same landscape, they actually require you to write sort of like special comments in your code that it then reads out and can use that to generate tools. These also can generate a lot of code. So the actual result of all those macro expansions will be basically the same thing as what we did ourselves in the method 1. So as you can imagine, there might be also stuff that gets added in those expansions that, in the interest of being very general, you might not want, or might be hard to debug if something goes wrong. So there's an older tool called Swig that sort of garnered a reputation for generating like megabytes of code on your behalf when you might not actually need a lot of it. So the third method and the last one that I'm really going to talk about is actually sort of, it's in some sense the highest level and in some sense the lowest level of all three. And what this is that most languages, so at least as far as I know, R, MATLAB, Julia, Python all support this. And my guess is that most other languages that have a pretty big use base probably support this because a lot of them are implemented using methods like this. They have a way just in the standard library to just load up a shared library with none of this specific stuff to your language and call functions into it. And so that's where we're going to go over here. So in Python, this is the C-types library that comes with the Python standard distribution. And I can show you what the code looks like here. So what we do is we essentially just have to tell C-types, like here's a path to my shared library. So this is actually a bit different than what we were doing before, where Python just knew where it was. Now you have to tell it. So that is one sort of contrast. But then after that, I can just say, OK, I know there's a name called Euler. And then I have to tell it the argument type here. There's only one argument. It's a C int, and the return type is a C double. And then Python will do the rest of the translation in the Python layer for me. And this is the sort of thing that would be very similar in Julia. The syntax is a little different. In Julia, it's called libdl instead of C types. But you're using the same shared library and doing all the same stuff. So just to sort of prove my final point, I'm going to go into here. I have only 2 files here because I'm not actually building anything. I'm just going to reuse that shared library from the earlier demo. I should say that here I'm including that C++ version where I wrapped everything in extern C. I could have also included the C version. They would work the same. And now if I run Python test.py 100, I get the same answer as before, which is a good sign. And this sort of works. And this is a very minimal amount of code I had to write to actually get this to be supported. And so I think the greatest thing about this method is how relatively simple it is. And that because it's very simple, a similar approach exists in basically every language I've ran into. So I list a few of them here. Julia has a built-in package called libdl. MATLAB has functions called load library and call lib. R has a function called .c, which is almost exactly the same, but as is usual with R, has a few weird bits that you have to work around. And you can reuse that same shared library between all these languages, because in the end, it's just written like that you would write a C shared library that you're going to link to on the command line. I think that probably the biggest benefit of this is that if you are interested in writing a package in something like Python, you probably already know Python, but you probably don't know the Python C API, or you don't know how to use PyBind. And so I think the great thing is that all the normal tricks or all the normal sort of Python stuff you'd like to do, you can use in writing this. It's really just using a library that's part of the language. It's not like learning this new other thing. Some cons are that, especially, I just had one function here. You can imagine if I had 30, then telling Python all of their names and all of their argument types and all of the return types is both kind of tedious and also a place where it'd be really easy to get something wrong. So if I just swap the order of 2 things, depending on what I do, maybe now I'm passing an integer, but it's being interpreted as a 64-bit floating point number, and you have to sort of check that later. I'll mention in a bit, there are some tools to sort of automate some of this that might help. And then I think another big con is that the library needs to be in a well-defined location that you need to be able to point to in your code. That's not going to be handled for you by the package manager for Julia or something like that. And so if you're already using a library that has a make install target that puts it in a well-defined place, you're probably already home free. You can just use that. Otherwise, you might have to use an environment variable or something where the user can tell you, hey, here's where to find where I put that built library. Yeah.
And so because you did extern C, the name was not mangled.
Yeah.
So then you can do lib.euler. But if you didn't do that, would you have to do lib._z5,
_z5, yeah,
whatever.
Yeah, and then it wouldn't work on Windows, right? So because Windows will mangle it to a completely different thing, which is this is sort of,
you have to know the mangled name in order to do this.
Yes, which is why you should use extern C. That the extern C sort of exists to make stuff like this possible.
I see.
And yeah, so you can work around it, and there are sort of various libraries that will sort of encapsulate what each compiler does for name mangling. So you could try to write generic code, but you could also just write a little wrapper that is extern C. And maybe all it does is just call another C++ function internally, but that's fine. Yep.
A templated function. How could you do it with this? Could you do something like list-like or?
Yeah, so templates, so and this is actually true in general for C++ shared libraries, you can't include a template, you can only include specific instantiations of that template. And so, and again, because you have to have unique names and you're using extern C, if you're sort of following along here, what you'd probably do, you could write a template that accepts say a scalar type, you want to have something that supports float and double. You should then write 2 extern C functions, one called, my cool computation _ float, and one called my cool _ double. And all they're going to do internally is just delegate to that template, but keep all that internal and make sure that your sort of external API is unique and well-defined. That make sense? Okay. Anything else? So this is sort of a transition point in the talk. At this point, I'm now going to talk not about these different methods, but about some sort of common real-world concerns that come up in FFI. And so if there's any sort of questions about what came so far, this is a good time. Yeah, Jeremy?
So if you care most about the end user having a successful time installing your package and you're willing to put in the effort, which of those 3 approaches would you choose?
That's a good question. I think so. Again, it sort of depends on what you care about. If you are, say, for example, you only have users in Python, then I think the best result is pick either of the first two options and then provide precompiled wheels for the user. Wheels are what Python calls like a compiled library. There are tools to like, you can have something in your CI that builds these for all the major platforms, then they just download it. They don't need a C compiler on their machine, which on Windows, most users will not have. If you care more about like, if you want multiple languages or different things, the easiest thing to install might still be, figuring out how this language specifically does it. It really is going to depend. Yep.
Yeah. For Babsy, I bind to a lot of languages, Julia, Python, and MATLAB, and others, and I write a single shared library with a single C interface, and then I wrote bindings for each of them, and I had to write packages for each of them that would install essentially like a wheel that would grab the specific version it needed of the binary itself and install it in a well-known location that it could always find it. So on the developer end, this is a huge pain in the neck, but on the user end, it's no big deal. But I find that there's not really a better option right now.
Yeah, so actually distributing this code, and this is a good point. Like there are, once you figured out how to call the code, there still is going to be the wonderful world of having users who try to install it. And that would be several other talks, I think. And I think Robert's a good person to ask. I also have done a lot of this. Like there is a lot of expertise here. Like, find your local software engineer and ask them. But yeah, that is a very good question. Yeah.
I guess this is another question along those lines. So this exposes, let's say, a function to the outside world. What if you want to expose an entire C++ class to the outside world?
Exactly the next thing I'm going to talk about. So if there's anything else asking now, otherwise I'm going to get into sort of more like real worldy examples. Yeah.
A simple way to deal with things outside of the public library. I'm thinking of how would you deal with NumPy, interfacing NumPy with C? Is it simple using this kind of interface?
Yeah, so that is sort of one Python specific thing. It does come up here. So the first couple examples, you could actually compile. NumPy has its own C API you could include and compile against. C types, the thing I just described, NumPy there's numpy.ctypeslib, which is a submodule of NumPy that includes a bunch of helpers for this. It'll actually come up in this example. Other languages that have a built-in array types, like Julia's vectors, will just naturally sort of work with this sort of thing. But NumPy, because it's not, it probably should have been built into Python, but it isn't. And so there is some stuff you have to work around. But that actually will be in one of these examples as well.
Essentially using the standard libraries plus and like that's all like reference counting and stuff. Is there an equivalent for that?
PyBind is probably the closest equivalent, yeah. Yeah, and if you look at like a PyBind file for a library in RCPP, they'll probably look similar. Just, in R, it's like that all caps sexpr thing, and in Python it'll all be called PyObject or what, it's. Yes, and so can PyBind compared to Python.h. Yeah. All right. So now I'm going to sort of just assume now that we're going to go with method 3, just to pick one of them and make it concrete. And I'm going to talk about, no matter what you do or no matter what your strategy is, there are certain things that will be sort of pain points or will be things you have to think about when you want to be doing this. And so one that just came up is object orientation, or more generally, what do you do about memory management between two languages? The first one, the one I have listed up here is A, just to keep them distinct from the methods, is like error handling. So in C++, maybe you're throwing exceptions. And I'm just going to tell you right now, it's a really bad idea to let those exceptions leave C++ and try to sort of stack unwind through Python. Bad things will always happen if you try to do that. But you probably do want to still have those exceptions show up to the user. So what do you do there? And then the third thing, and I think a lot of these concerns sort of fall under this thing, is like, if I have users in Python, they want to feel like they're writing Python. They don't want to feel like they're writing C. So for example, it's very common to write like out parameters where, in C, you're passing in pointers, they're being set into values. We don't really do that very much in Python. It's much more common to sort of return a tuple of multiple values. And so sort of thinking about on an engineering side, how do you sort of make it feel like the language that you like? Because presumably the reason you want to be calling your C code from Julia is that you like how Julia feels. And so if it doesn't feel right, that is also sort of a failure of the library there. So I have here, I'm actually going to sort of, now we're going to leave that example of the Euler function behind. I'm going to show you sort of a new fake library I made, and then we're going to talk about sort of time permitting all these different things that we can do with that library. So into the final example here, clear the screen. So if I show you, so I'm going to be working with this library I called foo very creatively. I'm going to assume a couple things. I'm going to assume that this library we can't change. So either we don't own it, or it's already been released as a C++ library, so we have backwards compatibility concerns that we care about. But this is sort of, this file is not going to be edited. And so there's a couple interesting things I try to, you can think of this as the equivalent of maybe you have some sort of object-oriented, like adaptive grid code or something like that, where it has a constructor that does some computations, and then later it has a compute function that you give it data, and it will sort of do something pre-processed to that data sort of thing. I sort of, to give myself an arbitrary challenge, I put a few things in here. So if you don't need to read C++ to follow this, I'll sort of walk through it. So it's an object-oriented API. So we're going to be creating objects and then calling methods on them. It uses exceptions. So if when you call this compute method, if you didn't give me enough data, I'm going to throw an error. And so I have to deal with that. And then the sort of third thing that is sort of like makes this interesting is that I wrote this as a C++ library, not really thinking about any of these issues. So I'm using these standard template library vectors, which I'm going to have to figure out how to translate those into Python. And so that's the whole thing. It's just doing a for loop and doing some sort of nonsense math. And then I'll also sort of show you what the target is. So I can show you test.py. And this is what I'd really like to be able to do, right? I'd like to be able to import NumPy. I'd like to be able to import foo, my library. I want to be able to make a new object with those X and Y arguments, same as in C++. I want to be able to create some data, as a NumPy array, whatever, call compute, get my output, print it. And then I'd also really like, if I give it something that would cause an error in C++, that should also show up as an error in Python. And so just to sort of prove that this can be done, in case I don't actually have time to show you all the details, I'll give you the repo link at the end. I'll just show you right now that if I run this, so with these arguments, I picked the result of the compute function actually computes the perfect squares. And you can see that here, it actually raises the exact runtime error with the same message that it would have raised in C++. And so now we're sort of getting into the details of how you do this. Now, if you've written a lot of C++, and again, this is not specific to C++, this would also be like if you're writing a Rust library or Fortran, and it uses concepts that aren't easily expressed through this really basic interface, you'd probably be doing something like this. The sort of thing that you might expect is that we're going to write sort of small, sort of C-compatible wrappers around this library. And so also in this directory, I have these two files called wrap_foo, which is, I can't edit foo.cpp, but I can write all the new code I want. So I'm going to write some new code, which is essentially that little library plus some extra helpers that will make it easier to call from whatever language I care about. So I'll start by showing you the header. Ignore everything above this. This is just to make C and C++ play nice with each other. It's not important to the talk. And now, so the sort of question of how do we deal with objects and these sorts of things is you turn them all into functions, right? This is essentially what's going to be happening in the end anyway, but you're just going to sort of do it manually. So I'll sort of talk through this. First, we have a wrapper around our constructor. And so it takes in 2 arguments. And then this other thing that I'm going to ask you to wait, I'll talk about that in a second. But it takes in the X and a Y, and it will give us back a pointer to the struct. And to make the API sort of private, I just have this empty type def with no struct there. Now, I hadn't previously talked about pointers, and different languages will have different levels of things. Like, Python, for example, you can actually write a struct declaration in Python and use the members of it. I generally recommend if you stick to everything sort of being opaque through a pointer, it will work in a lot of different languages. Because on the machines we care about, for the most part, you can really just think of a pointer as a number. And so even if your library has no way, let's say you're using some scripting language that has no way of talking about pointers, you can probably fool it by saying, oh, this function returns an integer, and that will probably work. I don't recommend necessarily doing that if you care about security and things, but it will probably work. So yes, yeah. So we also then have a wrapper around the destructor. So this class didn't really manage any resources, but it's still important to clean up memory if it did. And so this will just take in that pointer from earlier and basically call delete or free on it. And then we have a wrapper around that compute method. So it takes in the pointer to the object, and then I have replaced those std vector inputs and outputs with instead I now have a const double pointer, which is just my array of input data. I have an output pointer and then a length that is for both of those buffers. And then finally, I have to talk about this error message thing. So what I've done here is I've written a little struct, and I basically have this contract with myself / with whatever end user is going to be consuming this API of if one of these methods goes wrong, I will assign this struct, this double pointer to a new instance of this struct. And then you can call get error message on that struct, and it will tell you like, hey, what went wrong? And it's a struct because you might want more than just a message. You might also want to encode like an error type. Like maybe you want to separate between out of bounds errors and like another runtime error or something like that. And then once again, you have to free that memory. And so all I've essentially done is I've just taken that C++ API and all the stuff that C++ does nice for you and sort of unfolded it into a C API. And I think I have enough time that I can actually sort of briefly show you how I did this. It's not, it will be different for everything. These are sort of general rules around, there are lots of reasons why you might want to give a C API to code that is written in C++. And if you do that, you will probably do these sorts of things. It's not just for foreign function interfaces. But that error struct is just a wrapper around a C string. So there's nothing else fancy in there. I could put stuff in there later if I wanted to. Get error message just returns that message, and destroy error message just calls C++'s operator delete on it. So those are sort of bog standard. Creating a new object is just calling operator new to get a pointer back to it. But any memory allocation can theoretically fail, and so we also have to do error handling. And so for these sort of C interfaces, it's a good idea to wrap basically all of the code in a try catch. If you're calling C++ code, especially if you don't know if any of that C++ code wasn't written by you and it could throw an exception, you really want to catch everything. And so if it's a built-in exception to C++, we know how to get its reason out of it. It has this .what function. Otherwise, we just really catch everything and we just say, hey, it's an unknown error. And we just put it into that struct that we assign it to the pointer the user gave us. That compute method works the same way. We just have to sort of do this translation between you gave me sort of C-style buffers, but I have to turn those into C++ standard vectors. And so the input vector I can actually do just by creating a new thing by telling, hey, here's the pointer to the start and the end. The result, because it's sort of returned from the class, I just basically have a new result, and then I just do a mem copy into the buffer that the user gave me. I have been told that there are ways you can write your own custom allocators to avoid this. I've never tried it. So it is important to note that sometimes these choices do have overhead. So this has one extra copy compared to if you were just calling the C++ library directly. That is something to be aware of. Now, hopefully your C++ library is doing enough internally that overhead is sort of negligible by the time you're up at the Python level, right? If you're really doing real work in your functions, then a little bit on either end is probably fine to add. And then the error code is exactly the same as the constructor. Again, just catch everything. If I know how to get an error message out of it, I'll use that error message. If not, I still want to catch it to avoid it crashing my entire program. And then the destructor just to wrap around the destructor. So that's how I sort of it's a two-step process. I turned my C++ library into something that looks and feels like a C library. And now I can just show you sort of how to call that from Python. And so I have this file foo.py. And this is, again, using that method 3 that I described. So I'm going to use C types here. And as you can see, there's a lot of stuff. But all this stuff is just each of those functions in turn. I'm just going through, getting the name, telling you all the types of the things, and moving on, right? So this is actually to the question earlier. This is using the NumPy ctypes lib to create a pointer type. Now, I could have just said these were double pointers, but by saying that it's a pointer from NumPy, NumPy knows how to do certain checking. So like, for example, it will raise an error if you give it like a strided array, because we require that the data be contiguous in order to do this sort of pointer style. And so there's some extra features that are specific to Python. In Julia, the equivalent of this code would work just with Julia vectors, because those just naturally decay to double pointers, the same thing as like a C array does. And so I give a shout out here. I mentioned earlier that this can get kind of tedious, especially if you have a lot of functions. There are tools that will automate this step of it. So I've used before a tool called clang2py. It unfortunately comes from a library also called ctypes lib, but is not the same as NumPy ctypes lib. But what clang2py does is it uses the Clang compiler and its ability to parse a C header file, and then generates basically boilerplate code like you see after this line here. So it will generate, here's the names of all the things, the argument types, the return types. You can help automate things, make sure that you didn't switch the order of two things, right? You can use sort of your header as a single source of truth. And once you've done that, and actually, here's sort of the raw functions to call, you now have to do that sort of final step I talked about of actually turn it into something that feels like Python or feels nice to use. And so I bring back those letters here. I'm going to sort of go in actually reverse order of them. So we had an object-oriented API. Presumably that was for a good reason. My example was a really bad object-oriented API. It could have just been a function, but you probably have some thing that's doing some pre-computation or planning, and you want really an object-oriented thing. And so you should turn it back into something object-oriented in Python, so that that user mode still feels the same. And so we just write a class, and essentially all this class does is delegate to those functions that we created up above. And so in the constructor, we call that wrapper around the constructor and store the pointer as a result. If we didn't get a pointer back, then we call this handle error, which all it does is get that error message and then decodes it. Now, decoding it into a Unicode string will also perform a copy, so then we can clean up the memory of the error, and then we can give the user back, hey, here's the runtime error that happened when we were in the constructor. Same thing for deletion, right? So Python has a function that gets called whenever something falls out of scope. And so you want to call the equivalent destructor in C++. And so we write the same thing around the del function in Python, which says, hey, if I got a pointer during construction, if construction succeeded, then when it's time to destroy it, please free up my memory. And then finally, compute is, again, just sort of a wrapper around this thing. So the compute C function we wrote had this feature of having this out parameter, but we don't really want to do that in Python. Or you might want to have it be an option, but maybe not the default in Python. And so instead, I just take in the data, which I assume is a NumPy ND array. And then I can create an empty buffer of the same size, and then just pass both of them to the compute function along with their length. It will do its work, copy its answer back. And then again, if this failed, it will have told me, it will have put some information into this error. I can call it, and I can move on. And so that is how you sort of can go from, that's how you can sort of end up with that test file that we talked about here. And you can get the output that you wanted. So I just have 2 more slides, and then I should have some time if there are more questions. Went right to the end. OK. So I presented a few different options. You may be wondering sort of like, what do I actually do? And as I sort of alluded to, there are lots of trade-offs here. And so I think, for example, if you do really care about a one language-to-language pairing, you're not trying to support Python and Julia and MATLAB, one of these tools that I printed sort of in the middle, like PyBind, might be a really great match for your use case. But I think the important takeaway I want to give from this talk is that there's no magic in any of these, right? Every single one of these is using the same underlying mechanics of your computer. And so anything that's possible in one of them, you can do with the others. You just have to figure out how. And so, if you can figure out how to open a shared library and call a function in it in whatever language you're using, it can be a language that I've never heard of. If you can do that, you can, wrap an object-oriented API. You can wrap things that throw exceptions. You can do anything. It's just engineering at that point. So I really hate when talks sort of end by saying like, oh, it's all every option has trade-offs. You have to decide for yourself. So actually, we'll work in recommendation and say that personally, I always use method 3, and I see how far it gets me. If I run into problems there, then I might consider something else. This is partially because I often do care about writing. I want to write a Python binding, and then I want to write the equivalent Julia code. I know that the NVIDIA presenter got in trouble for this earlier, but this actually also is something that ChatGPT can help you with. I have had actually a success writing the foreign function binding code in Python and asking ChatGPT to turn it into Julia, and it actually ran the first time and passed all my tests. And like I said, there are also tools that are not sort of AI magic based that will help with this, like Clang to Pi and that sort of thing. And so they'll automate sort of that boilerplate. Turning that into a library that actually feels nice to use is still going to be up to you. But I'd also really argue that's the point at which you want to have opinions and you want to do it yourself. Because if a tool automates it for you, you might not like the choices they made or the trade-offs they made or whatever. This is also something where you can ask, we have a lot of software engineers on staff. This is the kind of thing that, especially if you already have a like reasonably well thought out C API around your code, then writing up one of these bindings is something that one of the software engineers can help you with. And it probably, like it's like a week project, not like a year project, And so with that, I will say thank you all for listening. So the repository is here on my GitHub page. You can also email any questions to me, or just find me afterwards. And I also wanted to shout out that on December 7th, the Scyware group here is giving a talk also about language interoperability. They're going to be highlighting, my understanding is they're going to be highlighting a tool that they're developing in-house that works sort of like PyBind. And I think also they're going to talk a little bit about the reverse direction of if you want to call, say, Julia code from inside of C++, the sort of direction I didn't talk about at all.
Thanks for a great talk, Brian. Any other questions? Chris.
So in many cases, I've seen it done with like PyBind, that you construct essentially your entire code base in C++, you call down into the library, and then you stay in C++ land and then kick back up at the end of the program, just to sort of give it the Python interface, or maybe you have configuration that's done cleverly that way. Do you run into instances where you want to kick the entire object back up to Python and then pump it back down into like a lower level language at some point so that you can pass the class back down into, like, say, a C++ type call?
I'm not sure. So I think it, what do you mean by pass the entire object back up?
So if you wanted to, let's say you have some C++ object, you have the bindings and everything, you do it in this functional form that you have it in Python, you construct this object, you use it. Now I want to pass that entire object to a completely different Python call, like go all the way back up to, say, the Python level, call something else, and pass that already constructed object down into something else.
Yeah, so if that object is storing a pointer, like the example I showed here, you would, when you call back into C++, you would just pass that pointer. And then the C++ routine is in charge of like knowing that that pointer is to that object and doing it that way. So yeah, this is sort of like writing C code. There is some sort of wild west of pointers, and like, because at the top level in Python, it's not going to differentiate between a pointer for one object and a pointer for another. So that's sort of, you have to be careful, or you have to use a tool that will automate it for you and make sure you get it right.
Yeah, go ahead. Yeah.
Just to check, does Clang2Py generate the extra Python head where you want that file?
No. Yeah, so it just generates the sort of bindings for you to get the boilerplate out of the way, and then it's up to you, because maybe you wouldn't want to wrap it up in an object or something. PyBind and those tools actually will create like Python-like objects if you use them, which is one advantage of them, if you're willing to deal with the other stuff. Yeah, Robert?
To push your repo, that's a dead link.
Oh, it's probably private at the moment. I'll make it public in like 30 seconds.
Okay.
But yeah.
Any other questions? There was a lot during the talk. Great. Thank you so much, Brian.